All right, hi everybody. How are you guys doing? How did the homework go on the first turn-in? Did everybody remember what to do with it and everything? No big issues then? Any questions on things before we get started on the new stuff for today? Yes, is Kristen. 20? Sure. So on 20, we're asked to prove whether these are odd, even, or neither. So I'd start off by evaluating h of negative x. So negative x, or negative of negative x squared is still negative x squared. Negative or plus negative x is minus x, and then the minus 1 just stays the same. And what I notice here is that this piece is not equal to h of x. It's not the original, so we know it's not even. And then if I try factoring a negative 1 out of this, that piece, after I factor the negative 1 out, is also not equal to h of x. So we know it's not odd either. So we can say it's neither. Okay. Anthony? Yeah, I don't remember what your guys' particular assignment was for. Kristen might have just been, I don't know. She asked me about it, so I did it. I don't remember what class is doing what, because the opposite days sequence. Some class had to do this problem. Maybe you guys weren't assigned this one yet. In which case, no big deal. But, Jason. Sure. So 14 asks us to state whether the labeled point is a maximum or minimum or neither, and identify the intervals which the function is increasing and decreasing. So a sloppy sketch of the graph you're given there. Looks something like this, right? So first thing we'll do is go through and look at the maxes and mins. So I noticed that there's only one maxima located here, and that's a local max. I know it's local because this end of the graph is pointing up, so there's definitely points on the graph that are higher than that one. This point is a local minimum, kind of for the same reason we have an arrow pointing down, so those points on the graph are definitely lower than that one. This spot in the middle is nothing, because if I look directly to the left of it, those are points that are higher than that point. If I look directly to the right of that point, those are points that are lower, so it's not a max or a min. Everybody okay there? Okay. However, if I look at that point there, it does appear the graph flattens out for just that instant at that point. So that will impact things when we talk about the increasing and decreasing part. So if I look at this, I see two increasing sections. I see this part of the graph is increasing, and I see that this part of the graph is increasing. Everybody okay with that idea? So increasing is basically if you're walking uphill as you go from left to right on the graph. So that first section starts at negative infinity and then goes to negative 3. And the second section of our graph starts at 2 and then goes on to positive infinity. Remember, when we're writing our intervals, we're always only concerned with the x-coordinate. For everything other than the range is the only thing that concerns a y. All these other intervals are going to concern only the x-coordinate. Now, it's tempting here to want to say that this is all one decreasing section. The problem is it's really two, because at that little spot in the middle that slopes out to 0, it's like a little flat section for just that one single point there. So I'm going to treat it as two separate decreasing intervals, which is kind of tricky. That first half of that interval starts at negative 3 and goes to 0. And then the second half of that decreasing interval starts at 0 and goes to 2. The thing we have to be careful about is at that spot at 0, the graph is flat, so it's not increasing or decreasing there. That's like a singleton point that's kind of constant. But the way we defined constant was we didn't define constant or increasing, decreasing on single points. So we're going to leave that alone for now. If you take a calculus course, we will extend that definition of constant to include singleton points, and they become very important in that course. Yeah, Ben.
For number 13, can we just do the decreasing function?
It's negative 2 to 3.
Okay, and my question is it inclusive? Right?
The increasing and decreasing and constants are never inclusive because of the way that we defined those intervals. So they are never, they're always parentheses. Mm-hmm. Josh. 12? Sure. So the directions on 12 say find the range for the given function and express your answer in interval notation. So it doesn't give us any direction of how they want you to find that range. So you use several different reasonable things you could have done to determine this. From your Algebra 3-4 course, you could have recognized that this looks like a radical function because it's in this form. And you might have remembered that the domain for these radical functions is h to positive infinity, and then the range is either k to positive infinity when the leading coefficient is positive, or it's negative infinity to k if the leading coefficient is negative. If you had remembered that, you would have seen that we're in this situation. So here's our k. So we could have just said the range is 2 to positive infinity straight away without having to do really any work. You'd have just recognized that as something you knew from last year. Now this is the very beginning of the year, and last year was a long time ago, so if you didn't recognize that square away, that's okay. Alternatively, another way you could have gone about this is looking at the graph, which is probably the easiest thing to do if you're just not sure what to do. So I would have gotten out my graphing calculator. If it wants to open for me. Which it doesn't appear to want to, so we'll use Graphmatica, I guess. I don't know what's going on, why it's being so difficult. but it definitely didn't want to do anything for me. Again, this is the same functionality as your graphing calculator, just looks a little different. And we'll do this real quick. Okay. Just copy that down over here. So if I do this, here's my graph. So I can see that one end is going on forever, but this other end like begins abruptly at this single point, right? Now if I look at just reading this off my X and Y, so I can say, okay, the range then, well, it begins with the Y coordinate 2, and that should be included because I have a point on my graph that has that Y coordinate of 2. And then it's going to be getting bigger forever because I have an arrow pointing up. So we have that. Okay there? Yeah. And now those are probably the two easiest approaches you could have taken for something like this, is to either look at the graph like we did here, or to remember that this was a specific type of function that we'd already studied about and use some of the properties that you remembered from last year. Does that feel okay there, Josh? Yeah. Are you sure? Well, you want to do it algebraically? I think this is the most confusing way to try to approach this, but we can try. So we have y equals square root x minus 3 plus 2. Right? Okay. So, we want to start by subtracting the 2 over here. And now you might think you want to square both sides, right? What's the issue with that, though? Well, before, can we plug any value of x into this? No, right? You can't plug in, say, 2 because you'd get a negative. Can I plug 2 into this, though? Yes. So we really have a problem there with that. So I wouldn't actually do this step. I would stop here. Okay? So if I think about the domain is 3 to positive infinity. So if I plug 3 in here, this side should be 0, right? So for this to equal 0, y would have to be 2, which kind of gives you the lower bound for the range. Does that feel okay? Yeah. And again, like, you can do these algebraically, but for the ranges, I think it's almost always, if you're not sure what to do, looking at the graph is usually the easiest way to approach it. Because you don't, it would be very tempting to square both sides and move stuff around and, do something for the range that's not quite right. You know what I mean? Okay. Any last calls on the homework, the previous homeworks? Alrighty. Well, let's move on here. Our plan for today is I want to talk about sections 1.6 and 1.7. So in section 1.6, we're going to be talking about asymptotes. And you guys talked about asymptotes a fair bit last year in your Algebra 3-4 class. In general, what we say is an asymptote is a line the graph approaches but does not cross, right? That was kind of our de facto definition here. Well, in the case of the horizontal asymptote, we're not going to differentiate between a horizontal end behavior and a horizontal asymptote. So by that, I want to look at this example to kind of differentiate for you guys what the difference is. So that we can explain what we're really saying here. I'll take the color version of this since I bothered to color code that stuff. Yes. Yes. Of course. Okay. So we said that an asymptote is the line the graph approaches but does not cross, right? If we look at this graph, using that definition, would y = 1 represent a horizontal asymptote? You should answer no, because we have a point here where the graph crosses that line, right? Now, in this course, we're not going to differentiate between those two situations. We're just going to, for the sake of simplicity, also refer to this as a horizontal asymptote, even though the graph clearly crosses here. Mostly for the reason that it's really difficult algebraically to tell when this is going to happen versus when it wouldn't happen, which you guys might have remembered last year when dealing with rational functions, that telling you the difference between a horizontal asymptote and just a horizontal end behavior, there wasn't really a good way of doing that a lot of the time. So we're not going to make any differentiation there. Is everybody okay with that idea? So just keep in mind that technically this isn't a horizontal asymptote, but for the sake of simplicity in this class, we're not going to worry about that difference. Okay? So we can, one question you might have is, how do we know that, like, way out as x gets really big, that graph isn't really going to cross that asymptote right there, right? Now, we can't, with the tools that we currently have, prove that it won't. If you take a calculus class, you might develop that technique, and if you take enough calculus classes, for sure, eventually you'll develop that technique. Why won't this open? I just don't understand sometimes. Well, why didn't it come up on top? I am so confused on how this thing behaves sometimes. You know, guys? All right. So if I go to the y = menu, I've already typed this in. Notice that the way I've typed this in, I got it to look just like a fraction. Do you guys know the calculator shortcut to have it do that? I see some people shaking their heads. In general, if you didn't know, if you press the alpha and the y equals button, that automatically opens up your functions or your fraction menu. And the n over d option is the one that gets you allows you to write a vertical fraction like that. Oops, didn't want to go that far. So I type this in, and I have my graph. And again, the question that we're trying to answer here is, how do I know that, like, if x gets really big or really small, eventually that graph doesn't cross, right? And we mentioned that we wouldn't be able to prove that, but we can create some pretty strong evidence. So what I'm going to do is I'm going to press second and the graph button and look at the table. So one thing you could do is you could scroll until your x's get really big. But notice I'm all the way out here in the hundreds. You guys, if you looked at your table, are probably in the ones and twos. And I'm not telling you to press the down arrow like 100 times, because that's just like really tedious and not a lot of fun. You can cause the calculator to skip things. So if you press second and the window button, that opens up the table setup menu. And you can say pick to have your table start at 1,000. So if you go back in the table, you notice that now our x value starts at 1,000. And if you wanted to, you could go to 10,000 or 100,000, and you could go really, really far down that x-axis, and you should see in all of those cases still, if you look at the y value, something that's bigger than 1. Everybody okay with that? And now that doesn't prove that it's never going to cross, but boy, that's some pretty compelling evidence that it's not going to cross, right? And enough evidence certainly for a class like this, where you can just pull some large values of x and show that, hey, it's still doing what we said the graph is still doing what we said it was going to do. And similarly, if you wanted to look at the negatives, right? If you went back to that table setup menu and instead wanted to look at starting at negative 1,000, you'll see kind of the same thing going on. That no matter how small of a number you pick, you're still going to get something that's technically below positive 1, which is exactly what we were saying that it's doing. Everybody okay with that idea? That if we want to verify something as a horizontal asymptote, that we can just pick progressively bigger or smaller, respectively, values of x and show that the graph hasn't crossed that asymptote in between. Okay? Do you guys remember the rules for rational functions on how to find your vertical and horizontal asymptotes? These are all things that you would have talked about last year, but let's review them, right? So for the vertical asymptote, to find that, or those, you just set the denominator equal to 0, and then you solve. Everybody's okay with that? So regardless of how your rational function is written, the vertical asymptotes are pretty easy to find. Your horizontal asymptotes are a little bit trickier. So if you have a simple rational function, something in this form, we know the horizontal asymptote is just going to be y equals k. If you have a more general rational function, something that's written as a polynomial over a polynomial, where the denominator is at least degree 1 and non-zero, there are 3 situations to worry about. So the first case is when the degree of the numerator is greater than the degree of the denominator. And I just abbreviated numerator as NUM and denominator as denom. In this situation, there's no horizontal asymptote. You might have remembered that in this situation, you have the slant asymptote or the oblique asymptote. This was the one where you had to do the polynomial division to get it. But there's no horizontal asymptote in that case. If the degree of the numerator equals the degree of the denominator, your horizontal asymptote is going to be the leading coefficient of the numerator over the leading coefficient of the denominator. LC is just me abbreviating leading coefficient. And the last situation, if the degree of the numerator is less than the degree of the denominator, your horizontal asymptote would be at y equals 0. And remember that when we say horizontal asymptote, we could mean just end behavior here also, right? So these things could cross in the middle, but the end should still be having that same asymptotic behavior where it gets really close but doesn't cross. All right, so example, let's just say we have y equals 3x over x plus 1. What would the vertical asymptote for this be? Yes, sir? So the horizontal asymptote.
Vertical asymptote, sorry. This would be x equals negative.
Very good. X equals -1. That's okay. Again, it's early, so that was definitely just didn't fully listen to the instructions. You know what you're doing. And the horizontal asymptote here should be 3, right? Because this is a degree 1 polynomial over another degree 1 polynomial. So this is the case where the degrees are equal, so it's going to be the leading coefficient of the numerator over the leading coefficient of the denominator. So 3 over 1 are just... Does that ring some bells? Good. Okay. Everybody feel okay about these asymptote ideas? For the most part, again, like the examples of things you'll have to do are going to be similar to things you'd seen last year, so it's largely review ideas, right? We reviewed again what the little rules were from our Algebra 3-4 class, kind of what we mean by an asymptote, but I didn't go into an extreme amount of detail on any of that because I think they're all things that we've seen before. And again, if you have more follow-up questions or anything when I'm doing this, please stop me and ask. It's okay to do that. I'd be happy to elaborate more. I'm just trying not to like completely reteach things that we've already kind of seen. You know, a lot of, I mean, you spent probably a good deal of time last year talking about rational functions, and I don't want to belabor that too much. We'll stick to reviewing the key ideas or the key rules on how to deal with things that I'd want you to kind of remember from last year. Do an example or two and kind of move on, especially here in the beginning when things are really kind of mostly review from previous courses. Obviously, it's fine if we need to elaborate on these. I will certainly do much more detail when we get into starting the trigonometry stuff. But for right now, where it's mostly review things, we're gonna I'll motor along through some stuff that's, especially when you guys say that you remember doing it last year. Okay? All right, so function operations. There are the four fundamental function operations. So there's addition, subtraction, multiplication, division. I'm going to be a little bit more technical here. So if we let f and g be two functions with intersecting domains, why do you think that we include this requirement that the two functions have intersecting domains? Actually, let's back it up a step from there. What do we mean by intersecting domains? Let's say for f, the domain was 2 to positive infinity. And for g, the domain was negative infinity to 5. Do those have intersecting domains? So Teresa, you shook your head yes. Why do you say yes? Great. So that was a positive 2, but it doesn't, I mean, still the same idea, right? So if I look at positive 2 to infinity, and then if I look at negative 5, or I'm sorry, positive 5 to negative infinity, there's values in common to both intervals, right? That's what Teresa's getting at. What would, in fact, the intersection of these two be? Well, it would be 2 to 5, right? Those are the values that are in common to both domains. Everybody's okay with that idea? That's what we mean by intersecting domains. Why would it be important the two functions have intersecting domains in order to add, subtract, multiply, or divide them? Well, let's suppose they didn't. Let's say f has the domain from 0 to positive infinity, and g has the domain negative infinity to negative 1. And let's say that I wanted to do f plus g of 1. Well, that tells me I have f of 1 plus g of 1, right? Now, f of 1 has an answer, but what would my answer to g of 1 be? This would be undefined, right? If you try to plug a value into a function that's not in the function's domain, there is no y value that associates to that. That x value is undefined. It has no partner when we paired our x's and y's together, right? Everybody's okay with that idea? So how do you add two functions together when one of the functions doesn't have a value? Does that make sense to do? No, not really. So that's why we have this requirement that the two functions have an overlapping domain. Everybody okay with that idea? Just because if they didn't, when we try to add or subtract or multiply or divide them, you can't do anything with that. It doesn't, it doesn't really make sense. Is that okay? Okay. Is everybody okay with the idea here that all we're saying is basically to add, subtract, multiply, or divide functions? You just basically are combining like terms like we've done before through most of our algebra and pre-algebra courses. We'll do a concrete example here in a moment, but okay. That's what those rules up there are saying. So let's take f of x to be 2x minus 3 and g of x to be the square root of x plus 2. And let's say I wanted to do f plus g of x. Well, from my rule above, I know that that's the same thing as just adding those two functions independently. So that's 2x minus 3 plus the square root of x plus 2. And at this point, I would look for any like terms to combine, but there aren't any. So I'm just done, right? Is everybody okay with that idea? What if we wanted to do g minus f of x? Well, according to the rule above, that's just going to be the same thing as g of x minus f of x. So I would just write the square root of x plus 2 minus 2x minus 3, right? Everybody agree with what I wrote down? You shouldn't, because that's not correct. What was that? Yeah, so remember that this negative sign is applying to the entire f of x. So when we write this down, we really need to put a parenthesis around it because we know that positive, when it distributes, it doesn't really do anything. But negative, when it distributes, definitely makes a difference. And as Abigail said here, that should be a +3 rather than a -3. Now, it's very easy to forget to do that. That's part of the reason I included this as an example. That had you not been reminded about this, probably half of us or more would have been oops-a-daisied that one. And that's why we wanted to, poke you a little bit at 8 in the morning and say, hey, not so fast there, hot shot. All right. Next up. Yes, sir. I do not. If you'd like to go to the bathroom, though, to get something, that would be fine. All right, so what if we have g times g of x? Again, and I know that's the same thing as g of x times g of x. So that's the square root of x plus 1 times the square root of x plus, x plus 2 times the square root of x plus 2. And what do I get when I multiply those together? Do I have to FOIL this? No. Good. I can really just think about it as the square root of x plus 2 squared, which simplifies to, well, almost. Think about it a little harder. You're missing something here. How about an absolute value? So you've squared something, right? The result of something squared, can that ever be negative? No. So that needs to have an absolute value around it. Because really you only can get positive results from that. You might have also recalled from way back when that one definition you had for the absolute value of x was like the square root of x squared, or the square root of, or the square root of x squared, either one. You might have remembered that from an Algebra 1 class or earlier, that's one way to define an absolute value. Again, not surprising that at 8 o'clock in the morning, after, a year away from doing this kind of math, that you forgot that kind of thing. This is part of the reason why we're doing these things as reviews. Not only does it help us review the particular skill of multiplying two functions together, but it gives me an opportunity to remind us of some of these other things that are easy to forget about, right? Okay. D. So let's say we're looking at the quotient f divided by g of x. Again, our rule says that I can just do f of x divided by g of x. So when I plug those in, that's 2x minus 3 over the square root of x plus 2. Everybody's okay with that? Anybody think that we should do more here? So some of you are shaking your heads. Why would you say you'd want to do more? Go ahead, Ben. Right, so probably somewhere along the way we've told you not to leave the radical in the denominator. What I'm going to tell you for this class is if that radical in the denominator contains a variable, like an x, you just leave it the way it is. If it contains just numbers, where maybe it was -3 over the square root of 2, that I would like you to rationalize. Or even if it's 1 plus the square root of 2, that I would still like you to rationalize. But something like this, where we have the square root of x plus 2, you can just leave it because it's not going to get any nicer looking. It's actually going to get much worse. So my argument would be that it doesn't really get any simpler. Everybody's okay there? Now these first four operations on functions should be very familiar with, right? We've done these things a bunch of times through pre-algebra at our Algebra 3-4 class last year. But it probably wasn't until our Algebra 3-4 class last year that we saw our fifth operation on functions. Do you remember what that one would have been? Not matrices. Starts with a C. It's composition. So remember that this little open multiplication symbol is the composition symbol. So when we see that series of symbols, we read it as F compose G. We don't say fog. Boy, that grinds my gears when students do that. It's like it's not an O. That's an open multiplication symbol. If you look at it typefaced, which I can't write in typeface, but I try my hardest to put that O like not on the lower line when you wrote your penmanship. Like fog should look like this versus F compose G, because the circle's in the middle of the letter instead of at the bottom, like you would for a lowercase o. I know it's subtle and it's hard when you're writing in penmanship, but there's no fog in math, right? So just so we know. Okay, so let's just do a little bit of quick practice here on doing composition again, because not that it's difficult, but if it's been a minute, it's worth kind of doing again, just to refresh our memory. So let's say we want to do F compose G of X. Well, from our definition above, we know that's the same thing as F of G of X. So I'll just start by replacing G of X with the expression that it's equal to. And now if I have F of something, what I do is I plug that something in to F everywhere where there's an X. So into F of X, everywhere I had an X, I'm going to replace that with negative 3x plus 4. So there were two places where I saw an X in my F of X. In each of those locations, I just took out the X and replaced it with that negative 3x plus 4. Is everybody okay there? Okay. Now let's simplify this down a little bit, because there's definitely some stuff I can do. According to the order of operations, the first thing I should do is take care of that exponent there. So if I want to do negative 3x plus 4 squared, that's just going to be like 9x squared plus 16, right? No! What do I need to do to take care of that exponent? You're going to have to make sure that you FOIL there. Very easy to forget to do that. Everybody okay? I'm just going to write out the FOILed response rather than show the foiling. Is that okay with you guys? And then the other spot I need to distribute. And then we got to distribute that 2 through. And then if we combine our like terms, we reach our final answer of 18x squared minus 39x plus 20. Yuck. There's a lot of symbol pushing there, but we survived. Yes, sir. So all I did was take everywhere where the x's were and I replaced it. Right? That's our definition for composition on how we do that. Okay. You're good then?
Yeah.
Okay. Yeah, of course. Again, when possible, I try to give like the briefest response possible. And if we're good, we're good. If it's not satisfactory, you can push me for more and I'm happy to give more, but I usually try to start with like the simplest pointing out thing I can do. Okay, let's do G compose F here. So that's going to be the same thing as G of f of x. So I'll start by replacing f of x with the expression that it's equal to. And then when I do G of something, I'm just going to look at my expression for G. And everywhere there was an x, I'm going to replace it with that expression inside the parenthesis. So we'll just distribute that -3. And then there's no more like terms to combine. So we're done. But there is an important takeaway right here. What do you notice from these two examples? Notice that they did not give us the same result, right? So important to note that in general, the composition of two functions is not commutative. That if you do f compose g and then you do g compose f, you typically do not get the exact same answer. You had another operation last year in your Algebra 3-4 class that also was not commutative. Do you remember what that was? Josh, I think you mentioned it earlier. It's matrix multiplication, right? So even if you like restrict matrix multiplication to like, so the dimensions of the matrices are both the same, so they both are square matrices, like a 2x2 times a 2x2. Even if you do that so that when I multiply both directions, it's both possible, and the result I'm going to get at the end is going to have the same dimension either way. Even if you correct for that, you still don't get commutativity unless it's under very special conditions. The same is true here. So in general, things are not commutative for composition. One of the special situations in which they are is covered in this theorem. So if f and g are two functions, we say that g is the inverse function of f if and only if the composition both ways is equal, and both of these two compositions need to simplify down to leave us with just x. Do you remember this theorem from last year? I think we used this a fair bit in Algebra 3-4 when we talk about inverses. Okay, we'll circle back to this idea here in a minute, but let's talk a little bit more about what we mean by an inverse function. So let's say we just have two functions here. So I'll call this function here in red f. If I wanted to draw the mapping diagram for its inverse, so I know what the inverse is going to do is it basically undoes whatever the function did. So the function takes 1 to 4, so the inverse should take 4 back to 1. 3 goes to 5, so I know 5 has to go back to 3. And then 2 goes to 6, so 6 needs to go back to 2. So the inverse of f should look like this. Is everybody okay with that idea? That essentially all we did on our mapping diagram is basically reverse the direction of everything, right? If I have a set of ordered pairs, so let's say this is my function f. How do I find the inverse for something like this? Yeah, I just switched the x's and y's. Very good. Now, if we compare these two examples, you'll notice something different happened in the results here. Just zoom that out so I can see both of them at the same time. So if I look here at the f inverse we got from the mapping diagrams, is that a function? Yeah, right? That's a function. If I look at the f inverse I got from the ordered pairs, is that a function? Are you sure? I see a repeated x coordinate, don't you? Oh, if you couldn't read it because of my messy penmanship, you get a pass on that. But those are both supposed to be 8s. It's not a function. So it appears sometimes these inverses will be functions, and sometimes they won't be functions. Would it be nice to be able to predict when we'll get a function versus when we won't? Yeah, and that's what our next set of vocabulary is going to be geared at. So we're going to do a couple of definitions. So we say a function is called onto or surjective. I'd say that those two words are used about the same amount depending on the textbook you're looking at. They typically will use one or the other. I'm going to present both of them to you because, again, probably in half the textbooks they use onto and the other half they use surjective. So even if you go beyond this course, it's nice to know that those two things are we're just talking about the same thing. So we say that a function is called one-to-one or surjective, or injective if every element in the domain maps uniquely to distinct elements in the range. And our last definition here says a function is called bijective if it is both one-to-one and onto. So let's go back and look at those two functions that we found inverses for, and look at whether they're one-to-one and onto. Okay? So if I look at this mapping diagram here to start, I know this function is onto because all of the ranges are mapped to, right? Every range gets an x paired with it, so it is onto. I can tell this function is one-to-one because each range is mapped to uniquely by an x. So because each one of those y values has only one x value going to it, I know it's one-to-one. Everybody okay with that idea? What is this reminding you of? Should remind you of checking to see if something's a function, but looking at the range instead of the domain, right? It's the same criteria, Just we're looking at the y coordinate instead of the x. Let's look at this next one. So we can say that this is onto because we don't know any better, right? We don't know what the whole range is if there's something that's being left out, but if you're just given a set of ordered pairs, like the onto-ness is going to be kind of assumed. Is it one-to-one though? It's not one-to-one because you have two y values, or one y value that's being mapped to by two different x values. So notice in the first graph, where the function was one-to-one and onto, its inverse was a function. In the second graph, or the second example, where it was not one-to-one, its inverse was not a function. This leads us to our another theorem today, where we say that f is one-to-one and onto if and only if f inverse is a function. Everybody okay there? Good. So we've shown how to write the inverse if it's a mapping diagram. And we've shown how to write the inverse if it's a set of ordered pairs. Let's do how we draw the inverse if we have a graph. So let's say you're given this graph. What I think is the easiest way to deal with this is I'm going to start by plotting. So we have 3 points labeled on our graph. I'm going to transpose or switch the x and y coordinates and plot those 3 points to start with. So I have -2, 5. So when I switch those, I have 5, -2. And I have 0, -3, so when I switch those, I got -3, 0. And then I have 1, -1, so when I switch those, I have -1, 1. Everybody okay there? Now what I'm going to do is, because this point 0,3 was like my vertex, I know that -3, 0 is also going to be like my vertex. So when I connect that, I have this graph. If you were to describe how we moved that the red graph to get the blue graph, how would you describe that change? Do you remember this from Algebra 3-4? It's a reflection for sure, but it's not just across the x-axis. It's actually across the line y = x. So that's where the reflection happens. Now, I think that's often kind of difficult to see. But if you just plot the points with the switched x and y values, it's usually pretty easy to come up with a good looking graph. But if you prefer to think about it as reflecting across that line, that is fine also. It's should get you the same picture. Although some students, I think, have trouble like seeing that reflection in their mind's eye. It takes a little bit more like spatial acuity or something to kind of see how that's reflecting. And it works a lot better if you're using, to see it the first time, if you're using something that's like a precise digital versus my hand sketches, which, you know, can be more or less effective in doing something like that. So if we look at this, so we have y equals f of x here. And then we have y, let's say y equals f inverse is the blue one. Notice that our blue graph is not a function, right? So if I look at f of x, was this onto? Seems fine. Was it 1-to-1? How can you tell? It was not 1-to-1. Ben, you shook your head. Okay, but looking at just f of x, how can I look at just f of x and tell that it wasn't 1-to-1? So if I draw a horizontal line, and that intersects the graph more than once, that means I have two separate x values for a given y value, right? So we'll have a horizontal line test that says if a horizontal line intersects a graph more than once, the function represented by that graph is not 1-to-1. And then you can conclude, since that function is not 1-to-1, we know then immediately that that function's inverse will not be a function. Is everybody okay with that idea? Okay. What if we have an equation? Let's say that we have f of x is equal to 3x minus 7. And let's say we want to find the inverse for this. This was something you did last year. Remember, this is basically a two-step process where you're going to get the x by itself and then swap the x and y value or variable. So usually makes it easier. Instead of writing f of x, we write a y there instead. So to get the x by itself, we'll add 7 to both sides and then divide by 3. And then we'll switch the x and y's. So we'd say then that f inverse is equal to x plus 7 all over 3. Everybody okay with that idea? So if I wanted to then prove f of x equal to 3x minus 7 and f inverse of x is equal to x plus 7 over 3, are inverses, I'm going to use that theorem from 15 minutes ago or so that said that two functions are inverses if and only if this is true. So I have two compositions to do. So let's bulldoze through those pretty quick. So that's going to give me f of g of x. So that's f of x plus 7 all over 3. When I plug that in to f of x, I get this. I have a times 3 and divides by 3, so those cancel out. And then I have a plus 7 and a minus 7. Those cancel out, leaving me with just x, which is what I need. If I go the other way, I have g of 3x minus 7. If I plug that in, I have 3x minus 7 plus 7 all over 3. The minus 7 and plus 7 cancel out. And then the times 3 and divides by 3 cancel out. And I'm left with x, which is exactly what I needed, both compositions to give us x. So that'll finish up here with section 1.3.